Alright, so part 3 of valence bond theory. We're getting near the end of this, so this video hopefully will be shorter than the others. I laid out for H2CO the Lewis dot structure. We filled in the hybrid orbitals. I just want to label what we have. So my sp2 orbitals, we said before that anytime a hybrid orbital has one electron in it, it's going to point straight at another atom and form a sigma bond. So these are going to be my 3 sigma bonds. One of them points toward the first hydrogen, one of them points toward the second hydrogen, and the last one points toward the oxygen. So I'm going to have a sigma bond, sigma bond, sigma bond between all 3 atoms. So I'm going to label that's a sigma bond, that's a sigma bond, and then to the oxygen, one of the 2 bonds is sigma. So I'm just going to say that's the one on the right is my sigma bond. Again, there's no real preference there. And then, so those are all making sigma bonds. So I can kind of label in my diagram, the hybrid orbitals are making sigma bonds. But then this p orbital that's perpendicular to the trigonal planar structure, that electron can overlap over the top and underneath. It goes top and bottom. But that's going to form what we call a pi bond. Pi bonds are not as strong as sigma bonds. So when I make a double bonds are not twice as strong as single bonds. Okay? The other thing is that if I'm making a single bond, 2 atoms extend, they can be a certain distance apart to get overlap between the atoms. If I have to form a pi bond, when I high five somebody, I'm going to have to step closer and so are they. Double bonds are always shorter than single bonds. Now, if I have to make a triple bond, in that case, I'm going to make the sigma bond straight between them. I'm going to make the pi bond for the second bond above and below. And then finally, if I want to make a third bond, well, the area in between the atoms is full. The area above and below the sigma bond is full. The only other place to make a triple bond is going to be around the sides. So in that case, I'm going to have a p orbital laying sideways, and it can overlap on both sides to form the third bond. Again, that's an indirect overlap because the atoms are kind of reaching around the sides to get to each other so the electrons can go back and forth. It's still not as good as the first bond, which is the sigma. So a triple bond is going to be a sigma bond first. You always form a sigma bond first between 2 atoms, then a pi bond, and then another pi bond. So sigma pi pi. All right, so let's do another example. Do C2H2. So if I do the molecule, now a lot of things I'm drawing in a minute, my last video on this topic, we're going to go to the PowerPoint and look at the pictures in the PowerPoint. That's going to give a much better 3-dimensional representation where you can actually see the pictures and see how the orbitals are overlapping. This is more what we have to do in class. If you're writing stuff down, this is how you're going to present things. So C2H2. If you draw that out, you're going to have to make a triple bond between the carbons. When we do valence bond theory, you always have to pick one atom to focus on. It tends to be the center atom, but in this molecule there are 2 of them. So really we can look at each one separately, okay? But I have to pick one to start with. So I'm going to focus on the one on the left, although in this case they're both essentially the same, but they won't always be. So that carbon atom, always look at the steric number. That carbon has a triple bond and a single bond, so that is 2 is my steric number. And I know my shape, if it's 2, the orbitals are going to go to opposite sides. That'll be my hybrid orbitals that go to opposite sides. That's going to be linear. So steric number 2, I think about my atomic orbitals. Carbon has the 2s and the 2 p's. If I only need 2 orbitals, I have to take the s, I have to take a p. So I've got s and p. If I'm using 2 of them, that means I have 2 hybrids over here. 1, 2, they're called sp orbitals. Then I have the extra 2p orbitals that are not hybridized. Carbon has 4 dots. We keep saying carbon has 4 dots. So when I come over to my hybrids, 1, 2, I have to decide, do I want to put my third and fourth electrons down here? If I do that, it's going to make lone pairs. I know in my structure over there, carbons shouldn't have any lone pairs. So putting the electrons there would not make sense. I have to bump them up and put them up here, number 3 and number 4. If I put electrons in the unhybridized orbitals, I know that those are going to make pi bonds. And I know that these are going to make sigma bonds. So in this molecule, I know that this carbon atom should be making 2 sigma bonds and 2 pi bonds. Let me look at my structure and see if that makes sense. This carbon, he's making a sigma bond to the hydrogen, and then one of these bonds to the other carbon is also a sigma bond. So I'll just say it's the one in the middle. The 2 pi bonds, one of them is a vertical pi bond going above and below, indirect overlap from the unhybridized p orbital on that carbon. The other carbon also has an unhybridized p orbital, and they overlap over the top and underneath playing footsies. So one pi bond forms above and below, the other pi bond forms around the sides. That way we know all the electrons are overlapping in unique areas. We're not putting too many electrons in any one place. Okay, so that's the overall analysis. Again, if I just asked you what's the hybridization, as soon as you know the steric number is 2, you just say, well, I take an S, I take a P, SP. If the steric number is 5, S, P1, P2, P3, you can never go above P3 because there's only a set of 3 p orbitals in any shell. So if the steric number is 5, it would be S, P1, P2, P3, D, SP3D. Okay? The highest we go is 6, so the highest hybridization you're ever going to see in this class is SP3D2. So that's our overview of valence bond theory. I'm going to cut off and we'll look at some pictures from the PowerPoint.